Hello and welcome to our presentation. My name is Tobias Klenze and this is joint work of Christoph Sprenger and David Basin. In this work we will talk about the formal verification of the secure future internet, in particular the forwarding protocols. But before I talk about future internet architectures, let's talk about today's internet. The internet is a network of networks. Each network is an autonomous system, as we call it, such as an internet service provider. And when two enters want to communicate, Alice simply selects a destination address. So she writes Bob into the packet header and hands over the packet to the network. And it's up to the network to decide which way the packet should be forwarded to reach Bob. Now, if there's an attacker that is on that forwarding path, the attacker can simply drop all messages. And Alice maybe notices that she's not getting any replies from Bob, but there's nothing really she can do about this. Even worse, the current internet is based on the border gateway protocol, which has no security built in. So an off-path adversary can also hinder the communication between Alice and Bob by launching a prefix hijacking attack. So this is clearly undesirable. In a secure internet, we would like to have that Alice and Bob can communicate as long as there exists an attacker-free path between them. And this property is provided by a number of recent proposals from the networking community. And one category, one class of protocols is called path-aware. So path-aware internet means that Alice not only embeds the destination address, but in fact the entire forwarding path on the internet into the packet header. It can still happen, of course, that there is a malicious entity on the path that drops the packet. But if Alice notices that she's not getting any replies from Bob, she can simply embed a different forwarding path into the packet header that hopefully avoids the attacker and ensures communication. And because these path-aware internet architectures are not susceptible to the same kinds of route hijacking attacks as the border gateway protocol is, we can ensure communication between Alice and Bob. So this is great. It gives end hosts a lot of control. But now what if Alice embeds this forwarding path here, which contains a loop? Well, clearly this is not a path that we should allow. And in fact, the only reason why Alice would do so is if she was compromised herself and she would like to incur extra costs on the internet service providers. So there's an issue of control here. We've given control in path-aware internet architectures from the network to the end host. But the flip side is that if the end hosts are malicious, then the network also needs to be protected from those end hosts. And this is exactly what this work focuses on. So there's two parts on how these path-aware internet architectures operate. First of all, there's the routing phase. This is where neighboring nodes exchange topology information and they construct forwarding paths, here in yellow. These forwarding paths are actually not just created, but they are also authenticated and authorized. So it yields a set of authorized paths. Each node on the path only authorizes those paths that it consents to being used. So when Alice now wants to select a forwarding path, she can only pick a path from this set of authorized paths. If the end host, the sender, tries to embed a different forwarding path which is not authorized, this will be detected by the network and the packet will be dropped. So the crucial security property of these architectures is path authorization. Packets can only traverse the network along the authorized path. And this is exactly the property that we verify formally in this work. Now there's a number of challenges with this. First of all, the set of authorized paths is created during the routing process, but each node can kind of decide by itself which path to authorize. So this set really is completely arbitrary and unbounded, and we cannot really assume much about it. In particular, also the path length is unbounded, which yields a security protocol and a property expressed over an arbitrary number of protocol participants. It's very hard to express this security property in an automated security protocol verifier. Thirdly, there's a large class of protocols. We don't know yet which of these protocols will eventually be deployed. So we would like to verify a large class and as many instances as possible from that class. So to overcome the first two challenges, we use a refinement approach in Isabelle Hall. So we simply take the set of authorized paths as an environment parameter to our models, meaning that we prove everything generically for them. We have an abstract model in which we easily can prove path authorization because it doesn't contain any attacker or any authenticators. We then refine this model into a concrete one in which we introduce both of them. In particular, we have a distributed colluding Dolof-Yau attacker model. Now, how do we show this for multiple different protocols? Well, the abstract and the concrete model are actually generic models. They abstract away from the particular security mechanisms employed by protocols. So in this way, we can really prove the security of a large class of forwarding protocols, and we also gain some insights in how these protocols relate to each other. These generic models have a number of parameters and a number of conditions. So these are conditions on the parameters, and we assume them to be correct in the generic models. And for each protocol instance, we then have to define what the parameters are and show that the conditions actually hold. But showing the conditions is rather easy. It doesn't involve reasoning about state transitions. So we can easily verify lots of different variants, and we've done so for 8 protocol instance models. So the nice thing about this is that the path authorization property has only to be proven once in the abstract model, and it is preserved in all the refinement and instantiation. So now I will dive a bit more deeply into how these protocols operate. So during the routing, the forwarding paths are created, and they are sequences of hop fields, one for each node on the path, and a hop field contains the local forwarding information delta and the cryptographic authenticator sigma. When Alice wants to send a packet during the forwarding, she simply embeds the sequence of hop fields into the packet header. As a packet traverses the network, it is being checked by the routers, so each router looks up its own hop field on the path and ensures that the authenticator was correctly computed. So this is a generic description of how these protocols operate, but they differ in a number of ways, in particular, most importantly, how the authenticator is computed. So a simple way of defining the authenticator would be as a message authentication code over the local forwarding data. The idea here is that everyone protects their own local data. And if we now write down a sequence of hop fields here in reverse order, and we visualize what fields are being protected by the authenticators, we can see that each of these boxes only protects a local hop field and they don't overlap at all. And unfortunately, such a protocol is not in fact secure. It does not ensure path authorization because an attacker can use hop fields from different paths and combine them in such a way that the resulting path is not authorized. So we have to do something more. And here I give you the example of what the Cyan protocol does. It defines the authenticator such that the MAC not only contains the local forwarding information, but also the authenticator of the next hop field, if there is one. So now if we write down the hop fields again and we visualize with the boxes what fields are being protected, we can see that there is some kind of chaining of these MACs going on. And even more so, if we write down the definition of sigma A, so of the first hop field, we can see that it contains delta A, so the local forwarding information. But if we further unfold the definitions, it also contains delta B and delta C. In fact, it contains the entire subsequent forwarding path. And we notice that we can define an extract function, which, given an authenticator, extracts the entire forwarding path. And this allows us to conclude the security proof more easily. Yeah, so how do we now generalize this, right? This was for a specific protocol. Well, we turn the definition of the authenticator into a parameter as well as the extract function because it depends on that. And in total, our parameterized concrete model has 3 different protocol parameters and 5 of these static conditions. So we had 3 verification challenges to overcome. First of all, there was an unbounded set of authorized paths, and we really needed high expressiveness because the path authorization property has a potentially unbounded number of protocol participants to it. And we also aimed to prove the security property of not just as a single protocol, but of a whole class of different protocols. And we have solved all of these challenges using refinement and parameterization in our Isabelle Hall model. There's a lot of future work. There's more aspects of these new secure internet architectures to be verified. So with that, I would like to conclude and thank you for your attention.